First of all, thank you. I'm actually very excited to give this talk. I'm very happy to give this talk. I don't get so much opportunities to talk about something like as basic as the stars. And actually, when you think about it, it's quite challenging to think what to say. Because I'm sure you heard before about the stars, and I'm sure you will hear in the future about the stars. And also, there are many more things than one I can say in a talk. So I had quite a challenge of what can I say? Can I say something which is important about the stars? And I had a lot to choose from, and I thought of something. So there is something important I want to tell you about the stars. But this important thing will have to wait somewhere to the middle of the talk. And until then, it's a secret, which is for me to know and for you to find out. But until then, let's start with some basic stuff. Now, I'm sure a lot of you know a lot about the stars, and I bet some of you know even things I don't know about the stars. So can someone tell me something basic about the stars? Yeah.
They fuse hydrogen atoms and therefore into heavier elements, such as helium, carbon, iron, etc. And that the heavier elements, that all chemical elements besides hydrogen have been produced inside stars.
All chemical elements besides hydrogen have been produced inside the star. This is a very interesting point. I will explain it a little bit more later, but thank you. That's a very basic, important point. Can someone tell me, this is very important. Can someone tell me something which is important but simpler to understand? Yes? Constellations of stars. This is something important. We can look in the stars and see that they have interesting shapes. I wouldn't trust this. I wouldn't trust this picture. For example, you can kind of see a star on the tree here. So I didn't take this picture, but yes, there are constellations. Yes, Ben? Thank you, Ben. So actually, Ben helped me make part of this presentation. You will see something he did, and that's an excellent point. Thank you, Ben. So maybe one of the most important, basic, simple facts that we know about the stars is that they're actually just distant suns. So you look at these tiny points, and they look just like tiny points, but actually, they're just like the sun. Now, how can that be? These points are very faint and small, and our sun is bright and big. It's just because they're very far. So stars are distant suns. The point looks so small because it is very, very distant from the sun. So this means that if we learn something about the sun, we learn something about the stars. And if we learn something about the stars, we learn about the sun. And this is very useful. The sun is close. It's easier to study the sun. On the other hand, the sun is only one guy. You cannot get a lot of statistical understanding. There are many stars out there. We can study the stars, and we actually learn a lot about the sun. Can someone tell me any other simple fact about stars? Yes? They have? Exactly. That was exactly what the next thing I wanted to say. Stars don't shine forever. They die. And there is a very simple reason for this. Earth, you have to pay for stuff. And the sun, at the end of the day, is a giant light bulb or a giant furnace. It produces heat. It emits heat and light. Someone has to pay for this. And there is a battery inside the sun, quite like this battery in a very principal sense, that supplies this energy. But like any other battery, it will eventually run out. Now, what kind of battery is it? And we have on the market many kinds of different batteries. There are many ways to produce energy. And in a sense, they are practically all of the batteries or all of the ways you usually think in day-to-day life how to produce energy are kind of like fire. They have the same efficiency of fire. They're chemical reactions. And if you would ask, suppose I fill up the sun with batteries, with wood, with gasoline, it doesn't really matter. I let it eat a lot of sugar. It won't matter. You will roughly get the same amount of energy you can have. And we know how much light is being emitted, and we can calculate for this size what's the time that it will take for the battery to end, and the answer is a few thousand years. And we know the sun must have been there more than that. For example, we know life is at least 1 billion years here, and life needs the sun. And it took a while to realize, but the answer is that it's a different kind of fire that is going on inside the sun. This is what this gentleman right here said. It's nuclear fusion. And nuclear fusion, roughly speaking, is 1 million times more efficient than chemical reactions. So instead of 1,000 years, you get billions of years. And this is what we need. This is how long the sun has lived. And this is roughly how long more it will live, a few billion years. But then energy will run out. The sun will turn off. And this is true for all stars. Some do it a little bit faster, some do it slower, but billions of years is a good number. So that's the second thing, which is basic, that we already know about the stars. They die eventually. Let me just say the essence of what's the difference between these chemical reactions that we see, like fire, like in a battery, compared to these nuclear reactions. So for this, well, it's kind of here. So I will use something from Robert discussed, that we are all made out of atoms. And there are kind of two basic things we can do with atoms. We can take different atoms and combine them and take them apart to form molecules and different compounds. These are chemical reactions. We take these atoms as whole, and we just move them apart and stick them to each other in different ways. This is chemistry. If we take the nucleus, and the nucleus is a tiny part of the atom. In fact, it is so small, it looks nothing like this. This is a really wrong picture of the atom. You can see some electrons, you can see some nucleus, but it's actually much smaller. So I put here a real picture of a big atom. You can see it here. Now, it's very small. So is there someone who cannot see this? Raise his hand. You cannot see this? You cannot see this? It's right here. You can't see this? You can see it? So it's actually, I didn't put anything here, because if I would really put the atom on this scale with the electrons with their size and the nucleus with their size, you would just not see anything. It's really tiny. But let's forget about that. Let's imagine this was how it looks like. Nuclear reactions take this tiny nucleus and break it and make new atoms from other atoms instead of just sticking them. And since the nuclear is so tiny, it has much more energy. How much more energy? Well, a million times more energy. There are millions of calories per gram. If you would eat a piece of sugar of nuclear energy, you would get extremely fat. Okay? It has a lot of energy. Okay, let's talk about other stuff. So we said suns are stars. What about this little piece here? What we are standing on? Is this a star? No. Yeah? No. How do you know?
Because it's made out of ground.
That's a good point, but can you see something? Yeah.
It's a terrestrial
Yeah.
planet.
It's a terrestrial planet.
It's not made of liquid.
Yes, Danny, do you have something to say? Yeah.
It's not very hot.
When what?
It's potential to be pretty hot, but
I can't hear you. Can you sit, Danny? Can you listen to this stuff? Thank you. Okay, so we said the stars are like the sun. We look at the sun, it's very bright. We look at Earth, is that bright? It's not bright. This is not a star. Now I put Earth here next to the sun in real size. Can anyone see it? No. You couldn't see it. Or maybe you could see something. It's tiny. Earth is a tiny, insignificant little piece of dirt. It has no effects of the star, and I will not talk about Earth much more, except for one point. There is something very important about Earth. What is it? Yes?
it's the only planet that we discovered that has life.
That's right. Maybe there is a lot of life in the universe, but we know there is life here, and life is pretty interesting. So in that sense, Earth is very interesting. Now, Earth is a tiny, insignificant ball going around the sun. If other stars are like the sun, do they have little dirt balls that go around them? And people speculated for millennia whether yes or no. They didn't know it, but it makes sense, yes. And actually, in the last 20 years, this was answered. Yes. We see tiny little dirt balls, just like this one, around other stars. And a lot of these, a few thousand by now, that we see in other stars, were discovered by this particular satellite after 2009. This is really recent science, okay? And of course, there are many aspects of studying these dirt balls and how they form, etc. But I think the driving force is just this question. Is there life out there? Is there? We don't know. We haven't seen any. But this is one of the main frontiers today of astronomy, searching for these dirt balls and asking, is there life out there? It's one of the main fields of astronomy now. Yes?
Well, actually, you could take a little dirt ball from Earth and it'll have a lot of life on it.
Yeah, that's another
So
thing.
technically, other dirt balls do have, they're just not nearly as big as Earth.
Okay. You're too smart for this stuff. Okay, so, but I don't have any more to say about these tiny dirt balls called planets, because for the stars, they're just completely insignificant. Okay? Let's talk a little bit about supernova. So what do we know about supernova? So look at this beautiful supernova. It's amazing, isn't it? Is this a supernova?
No.
It's amazing. What is that?
It's something like a galaxy.
It is a galaxy. This is not a supernova. This tiny thing is a supernova. This is a supernova. It's a little point. And for this, we need a big telescope. But this guy right here, he saw with his own eyes a supernova in the sky. And he shows you, look how it looks like. It's a star. It just looks like a star. It's just a new star. It's very interesting, but it's just a star. And you will be able to see a supernova just like this guy. It doesn't have very careful eyes. It's just that they're very rare. This one happened in 1572. He was very lucky. What's going on? He was a very lucky guy. If you're lucky, you will see a supernova like him. The only difference between this supernova and that supernova, this one is much closer. And it just looks like a star. Okay? So what's so interesting about this supernova if they're just tiny new stars? So let's look at a picture of this same supernova 400 years later. He told us exactly where he saw it. We can now go and take a picture of it today, of the same supernova. And this is what we see. We see a huge explosion. We know this one is already propagating for 400 years, and it's still propagating with full speed. How big is it? It's hard to explain, but I put the sun here for comparison. So we saw that the sun is much bigger than Earth, and you can see the sun right here. You see it? It's impossible to see it. This is so much bigger than the sun. This thing is gigantic. A supernova is a very powerful explosion. How powerful? And here I will use Robert's idea of how to explain what a billion means. So a billion is a big word, but just forget about a billion. Take a bucket of sand. That's not very powerful, but it has a billion little grains. So now I want you to take this bucket and take each of these grains and replace it with a... You have no idea. Very good. Yes, smart guy, yeah?
Atom undergoing nuclear fusion.
No. This time you're wrong. Replace it with another bucket of sand. What do you get if you have a billion buckets of sand? Does it look like this? No, this is, 50 buckets of sand. A billion buckets of sand, which is what you get if you replace each grain with a bucket of sand, will look like this. Do you see? This is a billion. They're just so dense you can't see anything. But I want you to imagine there are a billion buckets of sand right here. Now take each grain of each of these buckets, okay? And replace it with another bucket of sand. Well, I think I counted too much. Okay, let's count one back. Replace it with the biggest explosion you could have here on Earth. Thermonuclear explosion. So now you have a lot of nuclear bombs. Let them all explode. This is what you get. Let's summarize this and get it right. A supernova is a billion thermonuclear bombs. This is not 3 billion. It's a billion in terms of the energy. Also in terms of the mass, by the way, and that's very interesting. It has the same ratio between energy and mass as a thermonuclear bomb. Actually, since the sun is also burning nuclear energy, it has the same energy of the sun emitted throughout its lifetime of billions of years. This is emitted, in some sense, in a few seconds. We see it mostly in a few weeks and months. And it has the mass of the sun. This is why we think it's the explosion of some stars. Or this is one evidence that this is an explosion of a star. But later I will show you more direct evidence, okay, at least for some supernova. So supernovae are very powerful. Okay. Now, how do they explode? And here I'm going to do something that is maybe not good for such a talk. I'm going to say something which is very different than what you will most other astrophysicists will tell you and what you will find in books. I think the real answer is that we don't know. Now, if you will open a book about supernova, you will find answers. And they are very interesting ideas. But if you will read the fine prints, they will say, but they don't really work. Maybe we're missing some detail. I think they're missing the big picture. But we can argue about that. If there was somebody here, we could have a debate, which is actually more fun than a talk. I don't know if there is anyone willing to challenge and claim that he does know how stars explode. I think the answer is we don't know how they explode. That's the answer. Now, here at the Institute, we have a new idea. Actually, a couple of ideas how to explain how stars explode. And of course, we think we are right. At least about one of them, we have very strong arguments why we think we are right. And I'm going to maybe, if we have time, tell you about it. But I don't want you to believe me. This is the frontier. It's not knowledge. It's ideas which are being studied. The real knowledge, what do we know? The answer is no. We don't know how stars explode. This is one, I think, of the important problems in astrophysics. And because people think they know, it's not considered a problem. And this is actually very good for us, because now we can do it after a few decades. Okay. And here is a very important question. Okay, so stars are like suns, but they're very far away. Supernovae are powerful explosions. That's really nice. But are they important for us? Do we care about them? And the amazing thing is yes. Without them, and I'm not talking about our sun. Of course, we know our sun is important. I'm talking about the other stars. Are the other stars important for us? And the answer is yes. Without stars and without supernova, we couldn't exist. And this starts to bring me a little bit closer to the important point I want to tell you about. It's not that, but it brings me closer. But before we go on and talk about that, let's spend a few minutes to talk about things which are not stars, some other things that we see out there. Okay? What else do we see in the sky? This is not the subject of the talk, but we cannot talk about space without showing some other things. So I go outside, and I look to the sky, and except for the stars and the sun, what else do I see? Yes? We see our Milky Way, but it looks like a stripe of stars that here it's hard to see. You need to go to a very clear place. But do we see something like more direct, more clear? Yes? Whoa. You're going too far for me, dude. Too far for me. I'm talking about this. You've probably all seen it. You just need to pick up your eyes. It's there in the sky. And I'm not talking about the moon. I'm talking about this thing, which usually is not next to the moon, but it's really on the sky this big. Now, you must have seen it. It's right out there. Did anyone see this thing? This is called the Andromeda Galaxy. Did you see it? No. Actually, this is something you can see with your eyes on a very dark night, but it looks nothing like this. It looks like a little smudge on the sky. If you want to see this, you want to go up high where there is less air, preferably to space. And you don't want to use your eyes. You want to use a big telescope. But if you look at the same smudge that people can actually see without anything, with a big telescope, which is this particular one, is called the Hubble Space Telescope, which is just a big telescope in space. The mirror is this big, by the way. It's not so big. This is what you see. This is a galaxy. And this galaxy, if we look closely, actually has a lot of stars. How many? 100 billion stars inside this group of galaxies. And then this, as this lady just said here, we are inside another galaxy which also has 100 billion stars. Now let's look at some other galaxies. And the point here, the first point I want to say is, look at them. They're just beautiful. And they're just out there. And that other galaxy, the only reason we don't see it is just because our eyes are not sensitive enough. Imagine we could see it. You would look in the sky, the same sky. There are just marvelous things just standing there. It's just a little bit too faint. But if we had bigger eyes, we could see them. We don't need, and I'm not talking about points. I'm talking about big things on the sky, as big as the moon. Some of these are not as big as the moon. They're farther away. How many of them are there? So we take the Hubble Space Telescope, and we take a very dark patch so we can see far away. Okay? This tiny patch next to the moon. And this is what we see in this patch. Okay? It's not really close to the moon. The moon will blind the telescope, but it's as this size compared to the moon on the sky. And there are a few thousand galaxies here. All these patches are galaxies. Actually, kind of like the number of stars. And now, it's hard to take the telescope and take each one of these patches, but we can just take a few, see it's the same. Then we can calculate how much, just by kind of counting, how much of these galaxies are out there. And the answer is 100 billion. And this is a quick summary of the universe we can see. And here's an important point. We have no idea how big the universe is. There is a limit to how far we can see. And I'm not going to discuss why, but there is a limit. We can only tell what we see within this limit. The universe could be 100 times bigger than what we see. It could be 1,000,000 times bigger than what we see. Some people think maybe it's even infinite. We don't know. But within what we see, this is what we see directly. 100 billion galaxies. And in each galaxy, like our own, 100 billion stars. This is a quick summary. Of course, there are other things. Let's just say one slide about other things we see. I'm not going to discuss these. There are marvelous things out there. And a lot of them we don't understand. This, for example, is a galaxy. It's doing something crazy here. It's shooting these jets as big as a galaxy with 100 billion stars. I don't care what's the explanation. I think it's a mystery. Let's leave it at that. There are many things out there we don't understand. Okay? But let's go back to the stars. And we stopped at the point where I said that they are crucial for our existence. What do we mean? So here is a scientific fact. I think one of the most interesting, maybe almost as interesting as the fact you said, that we are all made out of atoms. We are stardust. Now, who said this? This hippie over here. She's a hippie. This is part of a song called Woodstock. And that's her name, Joni Mitchell. Is there any reason to believe her? And forget about that. Look at this. Does this look like a scientific fact? We are stardust. It looks like a line from a song. It is a line from a song. So let's look at a serious scientist. What does he have to say? And you can see it's very different. This is a scientific, serious fact. We are not stardust. We are star stuff. Okay? But what do they mean? How could we know? So this guy just said, all atoms heavier than hydrogen, blah, 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 were made inside stars. In other words, every piece of us, or most of the pieces of us, were made inside stars. Now, do we know this piece? Some astrophysicists took it and checked and found out it's made in a star. What do we really know? Because we don't really know this. What do we really know? So let me briefly say what we really know. What do we really know? Here is what we really know. We can look what we are made out of, and as Robert said in his talk, we are all made out of atoms. But what kind of atoms? There is a whole periodic table of atoms, but we are mainly actually made out of 4 atoms, mainly hydrogen, carbon, nitrogen, oxygen, and if you don't remember these names, it's not very important. Just nice to know it's only 4. That's it, roughly speaking, mostly. Okay? Now we look in the universe, and only one of them is common. Hydrogen, that's the simplest atom in the periodic table. It's 1 proton, 1 electron. It's actually kind of a proton. It's not even a real atom. This is what we find in the universe. Wait a second. Yes, you're right, Ben. Thank you. Very good point. It's not that we are 4 atoms. Of course, 4 atoms are tiny. It's 4 kinds of atoms. Thank you, Ben. H is the only one we see everywhere in the universe. Our sun is mainly made out of H. And we also have a theory, I don't want to discuss it, for how this H is formed. It's coming from the Big Bang. We're not going to talk about it. But where do these come from? And let's leave it as a question. But here's the fact we know. We know stars make these atoms. We know from our sun. We know from other stars. The sun is currently not making carbon. It's making helium. But that helium will later become carbon. She will make carbon. Will make carbon out of it. Other stars are now making carbon and nitrogen and oxygen from helium. This is a fact. So we know they're making it. That is a fact we know. We also know that some of them, as we said, explode. And we can see, when they explode, that they release a lot of materials, including carbon, nitrogen, and oxygen. And we can kind of count how much they release. And we can count how many times do these explosions occur. And then we can kind of count how much of these atoms are being distributed in our galaxy. And we can ask, is this enough? And the answer is, we don't know exactly, but we know roughly, and it's roughly enough. This is why we think that we are made out of star stuff. So to summarize it, or mainly there are other little bit more details, but this is the basic point. We know we are made out of these, and stars make enough. And this is the line. And of course, it has a loophole. I, for example, could have been put here by aliens. I don't know. Maybe they put life here and they dumped a lot of carbon and nitrogen and oxygen. We don't know. Who knows? But at least, since there are so many being naturally produced, probably this is the reason. Okay? Now, this is a fabulous story, I think. I like this story. It's a fabulous description, in a sense, of where we come from. It's kind of like almost a religious story. And here I'm now coming to the point which I really want to talk to you about. Maybe all of this is wrong. I'm just telling you blah, blah, blah things. How do you know this is right? Other people tell you other things. You open the Bible, it tells you really different things. That's also a very nice story. This is a very nice story. And this is, I think, the most important point I want to talk to you about. How do we know anything about these tiny points in the sky? How could we know? And there is an even deeper question. Could you even know anything? I have ideas, I have theories, but how do I know they're right? And I think this is the point of science. It's an amazing point. You could imagine we would never know anything about our universe. But the answer is yes, we do. We know things. Science lets us know things. Now, how is that possible? And I will not be able to convince you all of these things I told you. It's possible in principle, it's just too long. There is no chance in this talk. But I want to give you a few examples of things we know. And one of the central parts of what we know about stars, I want to explain how we know. Okay? And this is the most important thing I want to say in this talk. So let's start with let's warm up with some examples. Here is a very important question people were wondering about for millennia. What is the shape of Earth? And we can argue, and there are arguments. And it's amazing that the Greek knew and actually convinced most of the world, not all of the world, that Earth is round. But it's still, arguments. How do we know? Can we know? Does anyone know how we can know what's the shape of Earth? Yes?
Well, on the Apollo missions, when they went up in the moon rockets, they actually looked down and they saw big round.
Thank you. Exactly. Now we can take a picture. This is a picture. Now, does anyone have a doubt that Earth is not a cube? Do you agree that we know the answer to this question? It's round. There is no more doubt. And it's never going to change. Now, you could say it's not a perfect ball. I don't care. It's a ball. I don't care if it's not perfect. The question was, is it a cube? And it's not a cube. Is it flat? No. It's a ball. We know. How do we know? Because we looked. This is the most important part of science. Look, check, ask, do an experiment. This is how we know stuff. Not because someone told us, it's because we looked. And now I think you're convinced, unless you think I'm lying to you about this picture, but you're convinced Earth is round. There is no more question. Okay. Let's take a completely different kind of question. Actually, a question in math. And we can argue if math is science, I don't care. It's a question about our universe. And maybe some of you never even thought about it. I'm sure some of you did. Here is a fact. Let's look. We all know multiplication, but here's a nice fact about multiplication. What do we mean by 2 times 3? Well, we mean 3 2 times. So it's 3 plus 3. We all know how to calculate this, and the answer is 6. What about 3 times 2? Is it the same thing? Look, it's not the same thing. 3 times 2 is 2 plus 2 plus 2 3 times. It doesn't look the same, right? Even though here it kind of looks the same, but it's really something different. And still we come out with the answer 6. Okay? Let's check some other example. 3 times 4. It's 4 plus 4 plus 4. We can really count and we get 12. 4 times 3. Again, I'm just switching it around. But if you look, it's really something different. 3 plus 3 plus 3 plus 3. We check, it's the same number. It seems that when we do 3 times 4 or 4 times 3, we get the same thing. Let's check some other numbers. 7 times 5, you can check, it's easy. What about these 2 numbers? This is not so easy to do. You can do it with a computer. Okay? So we checked a few. So does this mean it's always true? Can we ever know? We can start checking each couple of numbers. Is it always true? Will we ever know? And the answer is yes, we know. And actually, I asked this question Ben, and I gave him a little hint. Look at the tiles on the wall. And he figured out. So let me tell you how we know. And the point here is that unlike the things about astrophysics, which I will not be able to fully convince you, here I hope I will be able to fully convince you. There is no more doubt. This is always true. And let's see why. Okay? Let's take an example, 7 times 5. And just present it a little bit differently. Okay? So I want 7 times 5. So I will take a row of 5 balls, and I will copy it 7 times. Right? So now I need to count 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5. This is 7 times 5. But what I'm really counting is just the number of balls in this rectangle. Rectangle. Sorry. But now, since I have 5 rows, in each column, I now have 7 balls. How many columns do I have here? 5. Okay? So I have 5 columns of 7. And this is the meaning of 5 columns of 5 times 7. So, and if I sum them up, I am again counting the same thing. I'm counting how many balls are in this rectangle. But Danny, honey, you're not helping me here. You helped me. I will show you. Danny actually took a video for this presentation. But by doing this, you're not helping me. Okay. Danny, Hamoud.
It would be an extraordinarily interesting thing if some sort of random phenomenon happened. That would be helpful, but not going to happen.
Yeah, things happen. We have to.
There's a very small probability that he will become a living example of a supernova, but that would be highly unfortunate in the probability.
And that will really help my talk. Okay.
But remember, there is always the probability that that TV will explode.
There is also that probability. Now, I'm not sure if you fully traced the logic. If you did, great. If you didn't, I encourage you to take it home, think about it, and get to the point where you're convinced. And then you have learned something for sure. You're sure of a new fact. And here is my most important practical. דני, בבקשה. אני מבקש ממך, אתה יכול ללכת לשבת בכיסא? זה מאוד מפריע לי, חמודי. זה נורא מפריע לי. דני. Okay. Here's the most important piece of advice I have for the younger people in this audience. Anything in math, and I'm not talking about everything in science, but in math that you learn in high school, in school, you have the power to fully understand it, to understand why it's true. And for science, it's harder. If your teacher tells you about the structure of an atom and you want to convince yourself he's right, it's a little bit hard. You can try to get the resources. For math, you can do it. You can fully understand any claim you learned in school. Do it. First of all, you will know a bunch of facts, but moreover, you will get confidence in yourself, and you will start to trust yourself that you have the power to be convinced. You have the power to understand something fully. Then you can take it back to science. Also, you will know a lot of math from this. Okay? So let's summarize what is science. Ask, look, and think. This is how we know stuff. And we shouldn't stop until we are convinced. And one of the important things is try to find many lines of evidence for the same thing. Don't get one. If math you don't need, but in science, try to find many things that tell you the same thing. Then you build your confidence. So let's try this out. Let's forget everything I told you about stars and start fresh, okay? And use the tools of science to solve what are stars, okay? So first, let's look. So let's stare at the stars. Look at them and ask, what are they? And you come up with, people did this. They came up with lots of ideas. It's fireflies, it's holes in some big surface. You can think of lots of ideas. You're kind of stuck. Okay, you need some more time, but you kind of get stuck by just looking at the stars. So we need to use some other tools. And the other tool is, again, let's ask a question. So the question, what are stars, is a little bit too hard to tackle. It's not quantitative enough. It's not something we can simply answer. Can we ask a little bit more modest question, but which will carry us a long way? And this, I think, this question that I'm about to ask, I think is the most important question of astronomy, in the history of astronomy. What is the question? What is a little bit more modest question than what are the stars? Something quantitative. Does anyone have any idea of the most important question in astronomy? It doesn't mean it's a complicated question. Usually the most important questions are very simple. You definitely can think about it. Any ideas? Yes? 1 times 1 is a good question. But something about the stars? Any ideas? Yes? Are you suggesting something? No. Are you suggesting? What are stars is our first question. But it's kind of too big a question. It's hard to, there are many ideas, but something we can measure. Yes?
How many of them are there?
That's an easy question, actually. We can count, but it doesn't really help how many. Some other quantitative question. Okay, and there's, maybe there could be other answers. Do you want to say something? No. I think this is the question. How far are the stars? If they're close, they're tiny and insignificant. If they're very far, maybe they're big and important. And how far is a quantitative question. 1 meter, 2 meters, kilometer, million kilometers. That's a good start. Ask the right question. And of course, we don't know what is the right question only after it made some sense. But this turned out to be the right question. How far are the stars? How can we ever know this? So we need to use some other tools, like our brain. Okay? And people did this. And actually, the ancient Greek did this. And they had an idea. How do we know how far is something? Well, there is a very simple trick. Move your head and see if it moves. And well, there are not too many things here, but you can still try it. Try to look at something that's closer to you and something that's farther to you. You see, when you move your head, things that are close seem to move very fast. Things that are far seem to move very slow. If, for example, some stars are farther than the other stars will move when we move our head. So let's look at the sky and move our head. Now, of course, the farther the thing is, this trick is less and less effective, unless we can move very fast. So let's try to move very fast. How fast? Should we run and look at the sky? That's a good idea. We can drive a car. We can ride an airplane. The Greek knew how to do something much better than the airplane. But first, let's see what happens when we ride a car. And this film was taken by Daniel. Oh, my God. There was not supposed to be any voice here. OK, you can hear Daniel talk also. Now, what I want you to focus here, besides this sticker of Angry Birds, is that we see many things in this picture. OK? And the fastest things are these trees kind of crossing the picture, right? The house there is also moving, but slower. This is fast forward. And the trees far away are moving even slower. This is the ideal. Okay? But to look at the stars, we need to move faster, and the Greek knew how to move faster. How can they move faster than a jet airplane? Does anyone have an idea? Aristotle had this idea. And I'm not sure he's the first, but he definitely said it. Yeah? Using? Did the Greek have a rocket? No. He actually did the experiment. He moved much faster than a jet airplane. Yes?
Well, if you stand on the equator, you're moving at about 14,000 miles per hour.
That's a good idea. Okay? We don't need to do anything. Earth is moving for us. We know Earth is moving around the sun. Aristotle knew Earth was moving around the sun. Did he? Let's assume for a second, yes. And he didn't know exactly, but he knew it's moving fast. It's actually moving 100 times faster than a jet airplane. It's okay, it's okay, it's okay. I'm fine. It's fine. It's moving very fast, faster than a jet airplane, 100 times faster. That's good. So he said, okay, and also if you wait longer, things have more time to move. Let's wait a year. We go to the other side of the sun. And he said, we're going around the sun. So we can go to the other side of the sun and look if stars moved a little bit compared to each other, which is the easiest thing to measure. And he did this experiment. And what did he find? Nothing. They didn't move at all. And here was an interesting question. We had a good question. He thought he had the right way to tackle it. He measured, he looked, he did all of the science things he learned in the book that I told him to do. And he's a real scientist, Aristotle. But here is what he got the conclusion. They're not moving. So there are two possible conclusions. He knew we are very far from the sun. Maybe they are very far away. But this is just impossible. He could not imagine stars are very far away, so far away, that we cannot see them move when we go around the sun. Or maybe one of the assumptions was wrong. Maybe Earth is not moving. This is a scientific conclusion. Earth is not moving because we don't see the stars moving. And we know someone is going around each other, either us around the sun or the sun around us. And we're talking about a year because we see, compared to other stars, that the sun is every time at a different place. So this meant to him that the sun is going around Earth. And this is what he said. I measured, and Earth is not moving, and the sun is going around Earth. And in many senses, he was right. He had also other arguments. If we are moving fast, there should have been a wind. We don't feel any wind. Earth is not moving fast. It's not moving 100 times faster than a jet airplane. It's not moving at all. We are at the center of the universe, and the sun and the stars are moving around us. But there are other ideas. Did anyone hear about Aristarchus? Really? Nobody really heard about Aristarchus? You heard? That's very interesting, because Aristarchus looked at the same data, same information. He didn't have anything else but his other thoughts. And he said, you know what? I think the stars are ridiculously far away. And I think the Earth is moving. And he had an argument. He knew kind of the distance to the sun, and he found that the sun is much bigger than Earth. He said, if the sun is bigger, who is going around who? The little guy around the big guy, or the big guy around the little guy? So he said, I don't care about this wind. I don't care about this ridiculously far. I don't know what that means. I think we are going around Earth. And since the stars are so far, maybe they are distant suns, like we know today is true. It's quite amazing. We don't hear much more about this guy. Actually, a lot of his books are gone. So we kind of know this statement, for example, only from people who refer to what he said. And actually, Copernicus read his book, or heard what he has to say, and he even cites him in his manuscript. Copernicus, if you don't know, is the guy in the modern times that first said that Earth is going around the sun. And he even cites Aristarchus. But in the manuscript, when he published it, he removed the citation. That's a very interesting thing, and I don't know why. He did it. But this guy, look, he saw 2,000 years ahead of his time. But at this time, this is a smart guy. This is a smart guy. They didn't really talk because this guy came a few years after Aristotle. But would you believe him or would you believe him? He has very good arguments. He had other arguments. If we are going, for example, if we are spinning around ourselves every day, from like in a carousel, you should be pulled out. We should fly off Earth. He was very smart, Aristotle. There were reasons for his claim. And this is a scientific debate, in a sense, and there was no way to tell. So good ideas and even good right thoughts are not enough. You need to show that you're right. Okay? Okay. What were they missing? And this is a little piece I forgot to mention when we talk about science. They were missing technology. They couldn't see the stars move. They didn't have the technology to see it. And this came very recently. We're talking about not, 200 years ago. This guy, Friedrich Bessel, at a rather old age for an important discovery, measured. He didn't see a penny in the sky. I kind of need to finish up. He just saw the stars move a little bit, the closest stars compared to other stars. How little bit? Very little bit. Like a penny 10 kilometers away. That's a tiny bit. You need this kind of telescope. He had a little bit bigger telescope than this to see this. Okay? Now, other people measured. There is actually an even closer star. It's interesting that a few people at the same year measured for the first time that stars are really moving when we go around the sun, which means we can measure the distance to the sun, to the stars. And this is the closest star. And the closest star is very far away, ridiculously far away. 4 light years away. How much is that? Light is moving very fast. It can go 7 times around Earth in 1 second. Imagine what it can do in 4 years. This is the distance to the closest other star. And once we know the distance, we know how bright it is on the sky, we can calculate how much it is really bright. And the answer, it is 1.5 brighter than the sun. The same as the sun, roughly speaking. And we can measure other things. We can measure with other tools its mass, roughly, its radius, okay, the surface gravity. I don't show here, but its luminosity is like the sun. Its radius is 1.2 compared to the stellar radius. Its mass is 1.1 compared to the solar mass. It's really like the sun. Stars are really like the sun. Not all of them, by the way. We learned that there is a broad range of stars. But if you need to remember something, stars are like the sun. Let's just say one thing about supernovae. I don't have much time, but how do we know supernovae are the explosion of stars? And one thing we said, in terms of the mass and energy, it's the mass and energy in a star. But there is a direct way, at least for some of the supernovae, and this is by looking. We see a star, this, I don't know if you can see it, there is a red dot here. We see an explosion later. The explosion fades away, there is no star. We just saw that the star exploded. Star, explosion, no star. I don't think there is much more convincing evidence than this. But this is true only for supernovae come in many different classes. This is, in a sense, true for one class of supernovae. So it's not the full story, but this is very good. We know at least some supernovae. We are sure they are the explosion of stars. Okay? And now, I will not tell you as I said, we don't know how stars explode, but I just want in a word to say that here at the Institute, a group of us, which includes Doron Kushner right here, and Subo Dong, which is now in China, we have a new idea, a new claim of how supernova explode. We have kind of two ideas. For some of the supernova, we think they are, because supernova come in different classes, we think they are the collisions of stars. Two special stars, very compact stars, called white dwarfs, collide. And when they collide, they explode. Now, people realized before that if you collide stars, a lot of the difficulties are overcome and it's easier to explode them. But two things they didn't realize. They thought it's very rare for stars to collide, so this cannot be the explanation. We showed it's not very rare. It's actually maybe as common as you need. And second, the arguments of how much it works, they didn't realize how easy it is to calculate, and this is something mainly Doron Kushner here did. He showed it really works. When two stars collide, like these stars, they really explode. And then we found some ways to show it really looks like a supernova. So we think this is how what's called the type 1a supernova, which is actually most of the recorded supernova, we think this is how they happen. It's the collisions of stars. It's very different from what you will read in books, like stars eating up too much, getting too fat, and then exploding. We also have an idea for the rest of the supernova. This is something we are doing now, today. I'm talking about these weeks. We have an idea. It's actually not a new idea. It's one of the oldest ideas. People just kind of disregarded, forgot about it, but we just kind of read it. It's kind of like reading Aristarchus' idea. Now we are working on it. You shouldn't believe this other story. You shouldn't believe this story. Maybe we are completely wrong. Okay, what you really need to know is that this is an active research. We don't know how stars explode. But there is so much data coming in, and there are new insights and new viewpoints that, and this is a very subjective feeling, I think in a few years or decades, we will know how supernova explode. Now we don't. I think we will, and maybe some of you guys will solve it. Okay, thank you.